Welcome in video 10 on fair valuation. We have seen in general the definition of fair valuations, and we considered a special class, the class of hedge-based valuations. And we have seen that the class of hedge-based valuations in fact coincides with the class of fair valuations. Now we will consider another class of fair valuations, which are called the two-step valuations. And we will also show that in fact this class of two-step valuations coincides with the class of fair valuations. First, we have to define the derivative. We consider the vector of asset prices y in our probability space omega GP, and a derivative of y is in fact nothing else than a random variable of the form fy for some Borel measurable function f. Borel measurability is required to be sure that fy is a random variable. So in fact, loosely speaking, a derivative is nothing else than a function of the time one prices of the traded assets. Now, we could define that equivalently a little bit more mathematical. We say let fy be the sigma algebra generated by the asset prices y. A derivative then is in fact nothing else. A derivative of y is a random variable defined on the measurable space omega fy. Now we will denote the linear space of all derivatives of y by cy. Cy is the set of all, let's say the set of all derivatives. Important, the class of hedgeable claims, this was denoted by CH. The class of hedgeable claims, CH, is a subclass of the class of all derivatives. Not any derivative is always hedgeable, except if we are in a complete market, as we will see. Now we consider some examples of derivatives. The first one, Fy, is the expectation of S given Y. If we attach to any claim S, its conditional expectation condition on the financial information that will be available at time one, that's a derivative. Another example is the conditional variance. The variance of S given Y is of course attaching to any claim. It is of course a function of Y and hence is a derivative. The time one value of a trading strategy mu is also a derivative. Fy equal to mu times Y is a derivative because it's a function of Y. Now, let us define a conditional valuation. We have defined valuations, we have defined hedges, and now we define conditional valuations, which is in some sense similar, the definition, to the definitions of valuations and hedges. Or it follows the same lines in the sense that there will also be a conditional normalization and a conditional translation invariance, and that we will instead, in fact, attach something to any claim in which we are interested. So a conditional valuation formally is a mapping pi y from the set of all claims to the set of all derivatives, attaching a derivative of y to any claim S. So to any claim S, we attach a function of y, or we will denote this function by pi y of S, such that we will assume that pi y is normalized. That means that the derivative that we attach to the zero claim is the zero claim, and pi y is also translation invariant in the sense that pi y that we attach to S plus A, or the derivative that we attach to S plus A, is the derivative that we attach to S plus the discounted expectation of the zero, of the claim A. Examples of conditional valuations are then pi y of S is e to the power minus r, the expectation under P of S given y. This is a conditional valuation because it attaches a derivative to any claim S, and it is normalized and translation invariant. And then another example, if we start from a Hedger theta, we attach to any claim S the time one value of the hedge attached to S, but discounted until time zero. This pi y of S is also a conditional valuation. So conditional valuation is an abstract concept. You have to see it as we attach to any claim as a kind of value, but we assume, that we know the time one information on the traded assets. So let us assume that we know the vector y, the vector capital Y, then we attach to any claim as a kind of value. In some sense, this value is a random variable, or this value here is a random variable because it depends on Y. So it's conditional, it's a valuation conditional on the information, on the financial information that will be available at time one. Now, just as with the hedgers, we have seen, just as with the hedgers and with the valuations, we had market consistent hedgers and valuations and model consistent hedgers and valuations, and also fair hedgers and valuations. Well, the same, we will follow the same line for the conditional valuation. Okay. Then, so we consider the conditional valuation pi y. We will say that pi y is market consistent if pi y of s plus sh, or the derivative that we attach to s plus sh, where s is a general claim and sh is a hedgeable claim with underlying hedge u. That's the derivative that we attach to s plus the discounted value of the time one value of the hedge u. Or, in other words, pi y of s plus sh is pi y of s plus the discounted value of sh, because sh is equal to nu times y. Pi y is model consistent then if there exists an actuarial valuation pi such that pi y of s orthogonal is pi of s orthogonal for any orthogonal claim. So if we have an orthogonal claim, the derivative that we attach to the orthogonal claim is in fact pi of s orthogonal. So it's a constant. And we will then say that pi y is fair if it is both market consistent and model consistent. Here now we have some examples of a fair conditional valuation, or we have one example of a fair conditional valuation. If we have a hedger theta, a fair hedger, and with this fair, with any claim s, we attach the time one value of the fair hedge of s, and we discount it to time 0. That is, this pi y of s is a fair conditional valuation. You have to prove it by yourself that this is a fair conditional valuation. You have to prove it first, that it is a conditional valuation, hence normalized and translation invariant, and in a second step that it is fair, hence market consistent and model consistent. Now, a remark: for any market consistent conditional valuation pi y, one always have that pi y of sh is the discounted value of sh. That's easy to prove. In fact, it follows from the normalization and the translation invariance of the conditional valuation. Try to prove this by yourself. So if we have a hedgeable claim, the conditional value that we attach to the hedgeable claim is the discounted value of the hedgeable claim. However, suppose now that that we consider now fy is a derivative. It doesn't have to be a hedgeable claim. Well, then there exist market consistent conditional valuations pi y, and there exist derivatives fy for which pi y of fy is not equal to the discounted expectation of fy. So if we have a hedgeable claim, the conditional value that we attach to the hedgeable claim is the discounted hedge, but it's not necessarily true that for a general derivative, pi y of fy is the discounted value of fy. Let us have a look at an example to illustrate that this formula will not always hold. Here is the example. We consider a market consistent conditional valuation pi y of s is e to the power minus r, the mean variance hedge of s, multiplied by y. In case fy is not a hedgeable claim, one has that pi y of fy cannot be equal to e to the power minus r fy. Why? Because on the left-hand side, we have a hedgeable claim, and on the right-hand side, the claim is not hedgeable. So in this case, it is impossible that this formula would be satisfied. So the formula is not satisfied in this case. Then we have exercise 15. That is an illustration of fair conditional valuations. Show that the following mappings are fair conditional valuations. The first one is the one we call the conditional standard deviation principle. So pi y of s is the discounted value of the conditional expectation plus alpha times the conditional variance. So it is like we know the financial information that will be available at time 1. We condition on this information, and conditional on this information, we apply the standard deviation principle. The same holds for the conditional cost of capital principle, or it's a similar structure. We take the information, the financial market information at time 1 as given, and conditional on that information, we apply the cost of capital principle. So the first thing we have to prove is that these two principles are indeed fair conditional valuations. Let's have a look at the first part, the conditional standard deviation principle. The conditional standard deviation principle, first of all, we have to prove that it's normalized and translation invariant, or the normalization means that we have to prove that pi y of 0 is equal to 0. This is straightforward to verify. Pi y also has to be translation invariant, so that means that pi y of s plus h is pi y of s plus the discounted value of a. Well, this is also easy to verify. So given that pi y is normalized and translation invariant, we have already proven that pi y is a conditional valuation. Second step now, we have to prove that pi y is market consistent and model consistent. Well, let us have a look at pi y of s plus sh is by definition discounted value of the expectation of s plus sh conditional on y plus alpha times the standard deviation of s plus sh conditional on y. Now, if we look here, we condition on y, then we know sh. So in this expectation, we can bring sh out. And then what remains of this first expectation of the sum is the expectation of s given y plus sh. The second term, the standard deviation, here we calculate the standard deviation of s plus sh given the financial information. If we know the financial information, then the sh is a constant, so the standard deviation of s plus sh conditional is the standard deviation of s conditional. If we look at this formula a little bit closer, we see that in fact this is pi y of s plus the discounted value of the time 1 value of the hedge u, where u is the hedge of sh. And we have indeed proven that pi y is market consistent because pi y of s plus sh is pi y of s plus the discounted value of sh. In the next step, we have to prove that pi y is also model consistent. Pi y of s orthogonal is by definition the discounted conditional expectation plus the discounted alpha times the discounted conditional standard deviation, but S is an orthogonal claim, so we don't have to conditional y, as orthogonal is independent of y. So we get, in fact, here the pi of S orthogonal, which is the standard deviation principle. So indeed, we have proven that for orthogonal claims, the conditional valuation reduces to the value to an actuarial valuation. That's the first part. A second part of question 1, we have to prove that the cost of capital principle, the conditional cost of capital principle, is also a conditional valuation. You can have a look at it by yourself. We have to follow the same steps. We have to prove that pi y is normalized and pi y is translation invariant, which is easy to verify. we have to prove that pi y is market consistent, and we have to prove that pi y is model consistent. Then there is a second question to prove. Prove that for both conditional valuations, pi y of fy multiplied by s orthogonal is fy multiplied by pi of s orthogonal. So for both the conditional standard deviation principle and the conditional cost of capital principle, we have this kind of positive homogeneity formula. Pi y of fy times s orthogonal is fy times pi of s orthogonal, provided fy is non-negative, is a non-negative derivative, and of course s orthogonal is an orthogonal plane. Let us have a look at the proof of this part. Well, we will have a look at the conditional standard deviation principle, and you can by yourself have a look at the conditional cost of capital principle. Pi y of fy multiplied by s orthogonal for the conditional standard deviation principle reads as e to the power minus r expectation under p of fy multiplied by s orthogonal given y plus alpha times sigma p of fy multiplied by s orthogonal given y. Now, we know that if we know y, if we conditional y, then fy is known, so we can bring y in front of the expectation. So we have fy multiplied by e to the power minus r expectation under p of s orthogonal, plus, what can we do here now with the fy? Because fy is non-negative, and it is known if we conditional y, we can bring the fy in front of the sigma. So that's what we did also here. So we get indeed fy multiplied by pi of s orthogonal with pi of s orthogonal, the underlying standard deviation principle. So we have proven that this formula, pi y of the product is the product of fy and pi of s orthogonal, holds true for the conditional standard deviation principle. Try to prove it by yourself that it also holds for the conditional cost of capital principle. Now we are able to define the new step, a new class of valuations, which we will call two-step valuations. What is a two-step valuation? We will say that the mapping rho from C to R, so attaching to any claim a deterministic amount, a number, a value, it is a two-step valuation if there exists a fair conditional valuation pi y and an equivalent martingale measure Q, such that rho S is expectation under Q of pi y of S for any claim. So what we do essentially here in a two-step valuation, first we transform S in a derivative, and then we determine the price of the derivative. You could ask by yourself, where is the discounting factor? Well, the discounting factor is in fact in the pi y, because the pi y is a conditional valuation at time zero. So the discounting is already occurring here. Let us have a look at two examples. The two-step standard deviation valuation is defined as follows. In the inner step, we condition on the financial information and we apply the standard deviation principle, but then we end up with the derivative and then we price the derivative by expectation and discounted expectation under Q. The two-step cost of capital valuation has a similar interpretation. In an inner step, we first condition on the financial information available at time 1, and we do a traditional actuarial valuation, let's say, by using the cost of capital principle. But of course, we end up with a derivative, and this derivative is valued as the discounted expectation under a measure Q. Notice that different Qs might lead to different outcomes, of course. So, I mean, the definition rho of S define the outcome depends on the choice of the Q that you will make. This was also presented, this theory, in the Université d'Abomey-Calavi in Benin in May 2017. And as a proof, you see that here the formula is indeed expressed, the formula of a conditional valuation. Now you can prove that the class of two-step valuations is the same as the class of fair valuations. We had the same already for the hedge-based valuations. We introduced the class of hedge-based valuations, but it turned out that the class of hedge-based valuations is the same as the class of fair valuations. Now we defined another class of valuations, two-step valuations, but again, any two-step valuation is a fair valuation, and any fair valuation is a two-step valuation. Let us first try to prove this. The proof can be found here. Let us start from the assumption that rho is a two-step valuation, and let us then prove that rho it is a fair valuation. So we consider the two-step valuation rho s is expectation under Q of pi y of s. We have to prove that rho is market consistent and model consistent. Market consistency first. Rho of s plus sh is expectation under Q of pi y of s plus sh. Or, because pi y is a fair conditional valuation, is the expectation under Q of pi y of s plus the discounted value of nu times y, where sh is nu times y. This is because pi y is fair and hence market consistent. And we can rewrite this as expectation under Q of pi y of s plus discounted expectation under Q of nu times y, or this is in fact rho s plus nu times y. So we have proven that indeed rho s plus sh is rho s plus the time zero value plus the time zero price of sh. Second thing that we have to prove that rho is also a model consistent valuation. Model consistency, so we have to determine rho of s orthogonal. This is expectation under Q of pi y of s orthogonal. But now pi y is fair and hence model consistent. So pi y of s orthogonal is pi of s orthogonal for an underlying actuarial valuation. The expectation under Q of pi of s orthogonal is simply pi of s orthogonal. So indeed, we have seen that rho is model consistent as rho of any orthogonal claim is pi of s orthogonal. It's an actuarial valuation. Conclusion, rho is model consistent and market consistent, hence rho is fair. So this was the first direction of the proof. We have proven that if rho is two-step, then rho is fair. Let us now have a look at the other side. If rho is fair, then rho must also be a two-step valuation. Well, we consider a fair valuation rho. Rho can always be expressed as the time zero value of a fair hedge. This is one of the theorems that we have seen before. So there exists a fair hedger theta f such that rho s is the time zero price of the fair hedge of s for any s. Or we can rewrite this as the discounted expectation under Q of the time one fair value of the hedge s theta fs for s. Again, the fact that we can write a fair valuation always as the time zero price of a fair hedge, this is a theorem that we have seen some videos ago. Or this discounted expectation under Q of the fair hedge value time one value of the fair hedge of s can be written as expectation under Q of pi y of s, with pi y of s equal to e to the power minus r theta fs multiplied by y. And hence, we can conclude that rho is indeed a two-step valuation because this pi y is a fair conditional valuation. F we have seen. This pi y of s is e to the power minus r theta fs multiplied by y is a fair hedger. This was one of the examples of a fair hedger. And then there is an exercise. Let us consider the mean variance hedge-based valuation rho. So rho is the mean variance hedge-based valuation. So it's the time zero value of the mean variance hedge of s plus pi of the hedging error, where pi is a model consistent valuation. Now, rho is mean variance hedge-based valuation. That means rho is fair. And if rho is fair, it can be written as a two-step valuation. So the question now is, show that this mean variance hedge-based valuation can be written as a two-step valuation, so as expectation under Q of pi y of s for a certain fair conditional valuation pi y of s. That's what we want to prove. Let us have a look at the proof. Okay. So we start with rho s is the time zero value of the mean variance hedge of S plus a model consistent valuation of the hedging error. Or we write this as e to the power minus the first term, we write at e to the power minus r expectation under q of the time one value of the mean variance hedge of S plus, and then the second term here, we write this actuarial valuation, this model consistent valuation as a vector product of a zero coupon bond investment of pi of the hedging error, and we multiply this by the vector I. We take the expectation under Q and we discount with R. It's easy to verify that the second term here equals to this term. And now we bring together this first and the second term, and we get e to the power minus R expectation under Q of everything that is written in the red brackets multiplied by y. And everything in the red brackets here, we call it mu s, and mu s, this is now a fair hedger. This here is a fair hedger. Why is that? Because we start from a fair hedger theta, we start from a fair hedger theta mean variance, we add a zero coupon bond investment pi of the hedging error, where pi is a model consistent valuation, then we end up with a new fair hedger. This is a lemma that we have seen some videos ago. So we can say that indeed rho s is expectation under Q of a discounted value of a time one value of the hedge mu s. Now, we have that this e to the power minus r mu s multiplied by y is a fair conditional valuation. Hence, rho is a two-step valuation. We have proven that rho is a two-step valuation. Okay. Now, let us assume, but we make this assumption only on this slide. Only on this slide, let us assume that any derivative of fy is hedgeable. So in general, this is not assumed, but here we assume any derivative is hedgeable. Or, to say it a little bit more formally, we would say that the financial market is complete, of the traded assets, is complete in the probability space omega fyp. So if we take a sigma algebra, the sigma algebra generated by y, then any random variable in this probability space can be hedged. So our market is complete in this probability space. Now we can define a two-step hedger. What is a two-step hedger? Of the fair conditional valuation pi y. So pi y is a fair conditional valuation. For any claim S, e to the power r pi y of S is hedgeable, because we assume that any derivative is hedgeable. So if this is hedgeable, we can write it as the time one value of a hedge, and this hedge we will call it theta S, theta two-step of S. So again, this is a hedgeable claim. Let's write the hedgeable claim here now as the time one value of the hedge theta two-step S. We can define a theta two-step S, and this theta two-step S is always uniquely determined because of the assumption of non-redundancy that we have made before. Moreover, theta two-step, this theta two-step defined in this way, is a fair hedger. This is an exercise, that I will ask you to make by yourself. Prove that theta two-step is indeed a fair hedger. So it has to be normalized and translation invariant. It has to be model consistent and market consistent. By looking at this definition, it's rather straightforward to prove that theta two-step is indeed a fair hedger. So that means that if we are in a market where any derivative is hedgeable, then in fact we can always write the fair conditional valuation pi y as the, if we bring e to the power r to the other side, as the discounted value the discounted value of the time 1 value of a fair hedge for S, and we call this hedger here the two-step hedger. And that means also that our rho S under this assumption of completeness in the sense that any Fy is hedgeable, rho S, which is in general expectation under Q of pi y of S, can also be written as the time zero value of the two-step hedger for S. This is the end of this video.